So first of all, so we have several laws of wedge products that indicate how it works. Excuse me. So first, we have standard distributive law that applies to functions. So the idea being that if you have two forms, and then you take the product with another form, and then you multiply the whole thing by a function f. So where I use f, you can still take it to be a function just like you always have. Then what you can do is you can distribute the wedge product through the sum. So you're taking the wedge product of omega and eta plus and then what you can do is, all right.
Is it appropriate for the f to be on the inside of the parentheses there?
Yes, it is. Yes. Oh, okay, yeah. Here I needed to have it inside. Okay. All right, so f is only multiplying the omega 1. So here I can pull it out. I can compute the product of this separately, and then just multiply by f at the end. And so this wedge product distributes over the sum. So in that case, it's just like regular multiplication. Okay. You also have associativity. I'll do anti-commutativity a little later. So if you have several forms that you're taking wedge product of, and we'll do examples of all these shortly, you can evaluate these in whatever order you like. You should not change the order in which they're written. All right, you have to be careful about that. But you can go ahead and take a product of the first two and then work a third one in, or you can take a product of the last two and then pre-multiply it by the first one. So the usual associative law applies. Okay. All right. Then you can now functions you can kind of treat like constants in a way. Just like when you're computing derivatives or integrals and you have constants involved, like constant multiplying a function, you can always pull the constant out. The same thing kind of it works the same kind of way with functions. So if you have two forms that you're multiplying, and this one is multiplied by a function, you can treat the function kind of like it's a constant and pull it out. So what you can do is you can compute the product of these two forms and then multiply the result by f when you're done. Okay. So these are the standard laws that still apply. So a lot of things are no different than what you've seen. Also, so in general, here I have f times eta. So anytime you're just multiplying a form by a function f, you can just tack the function on. So it's just straight multiplication in that case. But the rules that are a little odd, we'll talk about those now.
Can you say that one?
Business.
Okay.
Business points.
Go for it.
All right. All right. Multiplication of forms not commutative. It can be, it depends on the order. So you have two forms, and this is order K and order L. Then, if you multiply them in reverse order, it's equal except for -1 to the K times L. So depending upon whether the product K times L is odd or even, it either will be the same or it's going to change sign. Now here's an example that's going to come up pretty frequently. Suppose you have dz, dx, dy is what you're starting with. Well, you'd like to get this in the proper order, dx, dy, dz. Well, for that, you have to do interchanges. So you can go ahead and interchange dz and dx. But these are both 1 forms, so the product of their orders is 1. So it's going to change the sign. But now you want to interchange one more time to put dz, dy in the right order. So you get dx, dy, dz. Because you're interchanging two 1 forms, the sign will switch back to positive. So that is your final result. So anytime you're twiddling dx's, dy's, or dz's, that will flip the sign. So that's the main consequence of this that we'll see. Now, if one of these forms is a 0 form, it's just a function, then you have commutativity. You can put the function in wherever you want and move it around however you want. It doesn't matter. It's not going to affect anything. And another extremely important law is this. dx, dx, dy, dz, dz, all are 0. The wedge product of two of the same basic 1 forms is 0. So that's why all the examples we're going to see, whatever expression you have, dx, dy, dz, they're always going to be distinct. If any ever come up where you get two of the same, it just wipes everything out. All right. All right. So this is a multiplication operation that's going to work for us. Let's illustrate it. So the main things to keep in mind, to make sure you get it right, are these 2 laws here. Everything else is really no different from ordinary multiplication. So I'm going to leave up those 2. Okay. So let's see, let's make up some forms here. Is x squared dx. Eta is sine y dy. And then, okay, now make another form 8. New will be xyz squared dy dz. So we'll go ahead and start multiplying these forms. So we have mega wedge n, so that's going to be x squared dx, wedge sine y dy. So what you can do for functions, you can just pull them out, like for constants. So we're going to have x squared sine y dx wedge dy. So that's going to be x squared sine y dx dy. Now I just spotted a typo in the notes where I don't have a specific function filled in. This is f g